luckily enough, till now, I help you to get hopefully good enough understanding about the background of data converters. And then we go for the design of DAC. What? DAC usually is simpler than ADC. And the second reason is some of the ADC, it needs DAC. And this is the reason why I teach you DAC first. But for many of the professors or textbooks, usually they teach ADC first, then DAC. But anyway, I hope you can learn more, understand more about data converter in this way. So what is DAC? Anyway, you have digital input. Sorry. You have digital input, and DAC help you to generate our analog output proportional to your digital input. Oh, that is what we want. Again, right? Digital input, analog output. Hopefully, they are linearly dependent on each other. Okay, that is what we want. What is the definition for LSB? I think it's a piece of cake already. Allow me to show you the easiest structure for such kind of DAC. And you already learned it from your microelectronics. All right, so this is through the help of the so-called summer 加法器. And many kinds of different inputs. Anyway, I think you know it already, right? In theory, I'm grounded instead of DC. Okay, don't be C. AC grounded, AC grounded. It is in the middle of your supply voltage. If you have positive, negative, it will be grounded. Really DC grounded. But if not, usually that is in the middle. Yeah, VCC and 0, right? That is half VCC. Usually. Okay, I don't care, I don't mind. Anyway, if the amp is ideal, 0 here, you have 0 there, and the input current will flow through. And according to KCL, Kirchhoff current law, all the current will be summed, then flow through. You get this. Okay, got it. Yeah, you learned it already from microelectronics. So what you get is, you can see the ratios are very important. V1 R, right? So the voltage will be amplified by 8R to 1R, right? The current by resistance become voltage, right? V equals I and R, right? So you have R, it is divided by 2R, then multiplied by 8R, so you get 4. A4 to 1. Congratulations, that is DAC. All right, piece of cake, but I can help you more. First of all, how about monotonicity? 单调性, right? Why? There will be something wrong according to your monotonicity. For example, something wrong here. After fabrication, it is not R. Instead, it is a little bit larger. That is the usual case. Larger or smaller, but definitely it is not R. So for example, after fabrication, R here becomes a little bit larger, right? But if you divided 8R by this, you only get 6. Oh, it's really upset. You can see. For the input, from 0, 0, 0, 0, and 0, 0, 1, and 1, 0. Okay, so I suppose all the others are perfect at current moment. So you can see after you apply 0, 1, 1, 1, oh, you get 7. Forget about this, okay? I only focus on magnitude. What is the next input? It will become 1, 0, 0, 0, right? But sadly enough, you only get 6. So what is the output curve? From the beginning, 0, 1, 2, 3, 4, 5, 6, 7, then 6 again. Okay? Monotonicity is violated. We have only 4 bits. If you have more bits, especially for such kind of minorly weighted structure, it's really hard to keep your promise for monotonicity. Sorry for that. Okay? That is the hardest part, the most difficult part for such kind of minorly weighted 1 to 2 to 3 to 1 to 2 to 4 to 8, blah blah blah. For such kind of 二进位全重视 minorly weighted structure, sorry, it's really hard to keep monotonicity. Okay? But right now I only tell you, if after fabrication this one gets some error, all the others till now are still ideal, right? Sorry, nothing is perfect. Nothing is ideal. You will get a lot of errors. So, for example, this is not perfect. For comparator or op-amp, I told you the most important specification for IC design is input offset voltage. Okay, so from microelectronics, you derive this already. The output, even you have 0, 0, 0, 0, the output is not 0. The output is this. So what's the error? Offset. Right? Right? And then, if this resistor is not 8R, you will get gain error. If it is larger, then the output will become larger. If it is smaller, so it is gain error, right? Again, each parameter I taught you in previous chapter has deep root. 冤有头债有主，所有我教你的东西都是有根据的。They are really important. They have some reasons I need to teach you. Okay? Offset error, gain error, monotonicity, blah, blah, blah. All of them, they have roots. They have reasons. Okay? So for ADC, we have 3 major technologies to implement ADC. First of all, the easiest to understand is voltage division, 分压. By how? Resistor string or resistor ladder. 电阻串或电阻阶梯吧 OK 电阻网 Anyway, that is the easiest case. In this way, monotonicity is guaranteed. But what is the problem? If you have higher bits, for example, only 10 bits, you need to have 1024 resistors. Wow. How can you match them? How can you match them? So I warned you already. Even you have such kind of very simple R string for your deck. The number, the first, the second, during layout, you cannot have this one. Okay, sorry. It will be really bad for you. Okay, so you have better maybe 1, 4, and 3, 2 or something. You need to randomize the sequence. That's it. Yeah. But how to generate the correct output? This is a very simple idea for you. Okay? For MSB, if it is 1, it means what? To upper part. Right? If it is 0, to lower part. Right? Piece of cake. So you can see, if it is 1, I go upper part. If it is 0, I go lower part. So you split the whole R string in 2 halves. Bingo! And then you say, hey, how about the next bit? No worries. You split this into another 2 halves. The upper for 1, the lower for 0. That's it. Bingo. Very simple idea. Right? Right? So in this way, the circuit It's really easy to implement. Bingo. But what is the problem? According to breakpoints, your breakpoints will become 0, 1 LSB, 2 LSB. It doesn't make any sense, right? If you hate large LSB, then you can have this. Bingo. 0.5, 1.5, right? It can help you to minimize the INL from 1 LSB to ideally half LSB. Okay? But how to do the layout? Again, I need to warn you. Hey, look, I have unit resistor. Then I cut the unit resistor to be this and that. No, ridiculous. Okay? On the contrary, the minimum requirement is I have unit resistor here, unit resistor there, and then 2 unit resistor connected in series with each other. Okay? And then again, you need to randomize. Yeah. Not the first, the second. No. Forget about it. That is what you need to know. Okay? How about the previous one? You have too many switches, so the delay, the latency will be too much. You can see, for example, you have all ones, 1, 1, 1. So the voltage here need to pass through the switch, then the voltage bubble to the output. The latency will become too much. All right? How to speed up the conversion? Here. For each node, only one switch to the output. Bingo. But you need to know which switch to turn on and all the others to be off, right? You need the help of such kind of address decoder. Okay? Yeah. That is in digital logic. 数位电路里面有一个位置 decoder 解码器。That's it. So for example, you have 3-bit input. You will have 2 to third power, right? You have 8 outputs, and only one will be on. Others will be off. That is the function for address decoder. Okay? In this way, in theory, you only need, for each node, you only need to paste one switch, then touch the voltage button. Oh, you can speed up the operation. But in practice, it causes two problems. First of all, you need extra circuit, digital circuit, but piece of cake for current process. The second problem is, for node A, it needs to face all the switches. Nothing is perfect. Each switch will have capacitance, parasitic capacitance. The capacitance up for node A, you have huge capacitance here. So from the beginning, you hope with such kind of structure you can speed up the operation. But sorry for that, because a huge capacitance here, right? It needs to be charged from the current, for example, here. And how to charge it? The current needs to flow, AC current, okay, to charge it through R and C. Wow. What? Again, you need to face the worst case. What is the worst case? Because C is the same. So you need to estimate the largest R, the worst R. The worst R in the middle. Because for AC current, right? All that, I don't care. Okay? the resistance to the top and the resistance to the bottom are connected in parallel. Okay? So, which is the worst case? In the middle. So, how much resistance here and there? You can do it by yourself. I told you already. Piece of cake, piece of cake. Some more. Oh, yeah. We don't consider that kind of 0.5, 1.5. Yeah. Have yeah, this one. Okay, and divide 2, right? But this and resistance connected in parallel. The overall resistance is divided further by 2. This is the reason why you get. Okay, and you have R and C. Okay, yeah. You have the frequency usually is 1 over large. That one is so large. The operation frequency will be limited. Okay, allow me to tell you what is the solution. This is the solution from Samsung. It is patented by Samsung. Okay, the very bad company. Okay, I forget about it. Anyway, it is called matrix type or folded 折叠式的 resistor string R string. Sometimes we don't say resistor string. We call it simply R string. Okay, folded just like sausage N 墙. You have sausage, right? How to pack it up? One folded by the others to pack it, right? So we call it folded. 你的折叠的 N 墙 N 层 Anyway, yeah, with such kind of folded structure. Okay, you can see this is unfolded. It is hand 画 N 墙 from the top to the bottom, right? But right, we would like to fold it. Just like this one. From the top, to the bottom. That's it. And for the decoder, you have 2. MSB, to select the proper, we call it segment. Okay? 1 segment, 2 segments. Anyway. So, the higher input means you need to select higher segment. So you can guess, for example, MSB 0, 1. What does it mean? 0, 1. You have the bottom 0, 0, and then 0, 1, 1, 0, blah, blah, blah. Okay? Okay? So, since this is 1, 0, so you have 0, 1, 0, 0 to turn the bottom second on. On for what? You can see the node voltage after you turn on. The switches turn on, turn on. You can see the node voltage will be connected to the vertical column, 垂直线. So we select the correct horizontal or row. We connect all the node voltage of the correct row to the columns. But which column will be sent to the output? It depends on LSB decoder. Right now, LSB is 1, 0. So, you have 0, 0, 0, 1, 1, 0. Congratulations. Yeah. So, this one will be turned on. Okay? That's it. And this one, turn on. That one, turn on. So, you get the node voltage here. That's it. Anyway, anyhow. Again, MSB decoder help you to select the correct row and connect all the node voltage of the correct row to the columns, right? And then the LSB decoder select the correct column connected to the output. That's it. Two major benefits. First of all, the size of the decoder will be reduced substantially. Be careful. The complexity of the decoder, for example, 8 bits. For previous one, the complexity is 2 to 8 power. But right now, only 4 bits, only 4 bits. So for this one, the complexity is this and that. And you have 2, right? So the complexity is only this. I promise you. The digital circuit, the total number of gate count will be reduced by 8 times configuration. The more bits, the more you can reduce. For example, for 16, wow, then you will reduce to, right, 32 times reduction in the complexity. Bingo. And then the second merit, it only see 1, 2, 3, 4 transistors. So the parallel in this case is reduced from 16 to 4, right? Right? Bingo. But there is one problem. I have no time to explain. So, yeah, just for you to check how good you understand the operation. Okay? What is the problem? They didn't tell you. Pay attention. From the top, from left to right. Then, wow, from right to left. From left to right. From right to left. Wow. From the larger to small. And then small to larger. Wow. What solution you can have? It means what? For example, for this one, you have you can say yeah, the smaller here 0 0 0 1 1 0 1 1. But for the top 0 0 0 1 1 0 1 1. Okay? With the same decoder, you will generate the same output. But you need two kind of sequence. From left to right or from right to left. I mean from small to large. Or from large to small. I don't care. I don't mind. How to solve the problem here? Okay. I will tell you the wrong solution. In theory, that is correct. Hey, you can say, no. I hate this. I can connect this to that. Okay, this to that. Right? Bingo! Everybody from left to right. The same. But it is not a good solution. Why? The wire from here to there will become much longer. Okay, and then I promise you, finally, you will get the quantization level look like this. 1, 2, 3, 4. Then 1, 2, 3, 4. Then 1, 2, 3, 4. I mean, you will get larger voltage difference between the segments. No. Okay? So what is the solution? Think about it. Yeah, if I have time, you guys, if you can answer me, I will get one more credit point for you. Okay, anyway. Yeah, at the end of today's anyway, right now we have 2 advantages and 1 disadvantage. But this disadvantage can be solved in digital domain. That is my hint for you. Okay, not in analog domain, no. In analog domain, no, it's no good. You need to solve that in digital domain, okay? Anyway, even though we have two major advantages, I can reduce the size, right? Reduce it, and reduce the parasitic capacitance, but you can see all the resistors still need to match to each other because the voltage is still from the maximum to the bottom. Okay? Each resistor, if the resistance is changed, you will have impact on all the others. Okay? So how to make the resistance doesn't need to have impact on all the others? Okay. This is a very good solution. We call it intermesh. Actually, again, use your eyes as camera. Oh, take a screenshot, a photo of this one, and then go to the next. What's the difference? This one. For all the others, you have segments, R-string, right? Between your rows, you have vertical R-string. This is for coarse voltage division, and all the others for fine voltage division. Okay? Okay? And if RC is much smaller than RF, you can see RC is in parallel with so many RFs. And RC is much smaller than RF, right? Right now, for example, 4 bits here, 4 bits there. So totally you have 16 RF in parallel with RC, but RC is much smaller than it. It's even smaller than 16 RF, right? So it means what? Overall resistance is almost equal to RC. That is the case. That is the point. Since the final result for each one depends on RC only, it is uncorrelated with RF. So the coarse R string help us to separate each RF string. Okay? Fine string, this is coarse, to the coarse string and fine string. After the help of coarse R string, you can separate, you can make the fine strings uncorrelated to each other. What do I mean? You only need to match 16 of them. You don't need to care. Ah, my RF, your RF, forget about it. We are totally uncorrelated. It will help you to much simplify your layout for RF. Okay, but again, nothing is free. You need to pay what? Power. Because RC should be much smaller. It means there will be a huge current from RF to the ground. Oh, really bad. Okay? To enhance your linearity, you need to pay power and chip area, extra chip area. All right? But anyway, this is a very good example. For example, Samsung patented this, right? And then you are smart. How can you get rid of that? Oh, you tell the court, you tell the IP office, look, I have extra component to enhance my performance. Anyway, all they have, all the components they have, you have. But I have extra one to enhance the performance. Bingo. You get another patent. All right? Do you violate Samsung's patent? Yes. Yes. But you are the successor to the court. You only need to pay very little fee because all the countries would like to promote innovation. You have extra component to enhance the performance, even though you violate the original one, but you only need to pay very little money to the original company. That is the best way out of such kind of patent war. Okay, not like Chinese, they simply copy and paste. They don't respect anything. But we are not Chinese. We need to be very careful. This is what I recommend you, the best way. Okay, so is it possible to get rid of all of them? I promise you, almost impossible. Otherwise, you will make your circuit really, really complicated. So you also do the same thing with Chinese. As Chinese, copy and paste, but with extra component to enhance the performance. Then you will get the succeeding patent, 下位专利. Then you can defeat the original one. Okay? That is the much better idea. And then you can go further. So, sorry, I need some more minutes. So, Tony, for the deck, it's up to you guys to have arch string. Maybe 3 bits, good enough. I mean, 8 resistors. Or they would like to have, how can I say, the current structure, current steering is also okay. Right? Yeah. Then I will discuss with you too to simplify the homework. Again, the homework is not used to turn you down. You cannot pass the class. No. The only purpose is to train you, okay? To realize, to implement the idea, to be good enough to get well prepared for your future design. That's it. If you do your job, I won't turn anybody down. Okay? Anyway. 所以不是拿来当各位的哈，只是要给各位基础训练，好好的面对你的未来。所以拜托大家务必要把东西交出来。Even though the performance is not good, it's still okay. It's still okay. Yeah. Don't copy the others. You are not Chinese. Sorry for that. Okay. I hate Chinese. If you copy and paste, I will turn you down. Okay. Even though I cannot kill you, but I will. Yeah. Anyway, I hate them. In this way, we can go further. How can you go further? You can see when I select, for example, if it is this one, then I only need to apply 5 voltage division through the help of this R string. For all the others, they can be turned off. So if I am the God, I check the MSB. I only need to have 1 fine string, right? If this one is select, then I attach the R string to this RC. If the MSB is here, so I move the R string here, right? In this way, I can get rid of all the other R string. Okay? Okay? And then, here comes the next. You only need 1 coarse string and 1 fine R string. But how to attach the fine R string to the correct coarse string? Through the help of switches. Bingo. That's it. This is the best example. Show. It can enhance the performance. Nobody will say This pattern violates previous. Oh, you don't need to pay anybody any money. Okay? Even better. All right? Why I love it very much, you can see it has many kind of contribution. Not only the circuit is simplified very much from the previous one, and also another innovation is here. For usual, I cannot say for stupid engineer, but for common engineers, not so talented engineers, yeah, you will see, the arc string will attach, for example, 0, 0, then the top, the bottom. If the MSB is 0, 0, 0, 1, they will shift to here, the top and the bottom, right? That is as a the fine here. Oh, what does it mean? For the next, the bottom needs to connect it to this node, right? So the switch needs to be doubled from 1 to 2. But you can see the authors are really talented. They connected this and that, this and that. In this way, you flip the R string. But you need to be careful. Again, the larger, the smaller, right? If you flip it, the larger, the smaller, you need to be careful. Because flipped, you will get the same problem. The previous two. And again, what is the solution? In digital domain, think it by yourself. If you cannot think it, next time when I come back, yeah, you can ask me what is the solution. But I hope some of you will figure out how to solve it. Okay? Yeah, piece of cake. All right? With such kind of flipping, yeah, upside down. You can reduce the total number of switches here by 50%. Wow. But again, nothing is perfect. Even with such kind of very innovative circuit, there is still some problem. The major problem, put on this. When you attach your fine string to your coarse string, you cannot let it know, hey, somebody stand beside me to reduce my resistance, right? If the resistance is reduced, oh, sorry for that. You will get what? For example, you will get when you are attached, you will get smaller resistance, right? Smaller voltage division. It doesn't make any sense. Okay? To prevent any kind of load effect of the fine string from the coarse string, you need a voltage buffer. But what will going wrong? VOS. The VOS here and the VOS there, supposed to be not the same application. So two ways. First of all, to reduce the VOS much smaller than your LSB. Bingo. But it's really hard, very expensive. And the other one, try your very best to match the VOS of this to that. Okay? If the difference from VOS1 and VOS2 is, again, much smaller than one LSB configurations, you can make it. Okay? So, right now, the pressure, 压力 of design is put on open design instead of resistor layout. Got it? Okay. Bingo. That is what I can help. So you can see a lot of innovations for humankind. How many years we make it? I promise you, more than 10, 20 or 30. Within 20 or 30 minutes, I show the history of humankind's for arc string, for voltage division deck. Okay? For each new idea, it takes years to realize it. Yeah, that is our history. So hopefully, in the future, some of you in the class will help us to create the other innovative circuit to enhance the, again, to enhance the performance and also reduce the circuit complexity. That is what I encourage you to do. If you make it, you don't need to design your circuit. You simply collect money from all the IC design houses. Good enough. All right? So this is the end of voltage division deck. And how about the others? I don't have time. Yeah, I cannot torture you too much. All right? Even though I would like to share more experience, more knowledge with you, but time is limited. The other two, for example, we call it charge redistribution, or sometimes we call it charge sharing with capacitors. Sometimes we call it switched capacitor. Okay? And the third one is, okay, forget about that. This is for low power. If you would like to focus on low power design, only one solution is this. Okay? If you would like to focus on faster speed design, then R string. Oh, no. Even better is current string. Sorry. This is in the middle. The easiest one is this, but the fattest is current string. We call it current steering. 3 major architectures. Okay, so this is the end of today's class. 2 weeks later, I will finish this chapter for you because we need to go further for even more complicated ADC. And then, at least I hope I can teach you PLL and DLL. And for the others, read by yourself. Sorry for that. I do extra job already, much more extra job, but time is too limited. Okay, to conclude today's teaching, I would like to show you the last slide for today's class. This is from Broadcom. Broadcom actually, in previous era, that is the best telecommunication IC design house, even better than Qualcomm. But I told you already, it focused too much on wired communication. It has huge success for ADSL. Okay, it dominates the market, the worldwide market. But Qualcomm focused on the other side, wireless one. It is wired, and that is wireless. And right now, Qualcomm, I guess, is much better than Broadcom. But Broadcom would like to buy Qualcomm. A few days ago, it is rejected by American government. Okay, because wired and wireless, it will become a monster to kill all the others. It's, for such kind of monopoly, 垄断, 独占, is no good for market competition. Anyway, in the past, or even now, it is still the best for wired communication. Yeah, you can see this is the revolution for tech design. Yeah, with 0.5, 0.35, 0.25. This is the best wired communication IC design house. You can see the chip size is scaled down. Congratulations. But before the end, another information for you to refer is, if you change the title, 10-bit kernel mode or any kind of mode ADC, I will show you another slide. In ADC, they are almost the same. Okay? That is really upset. It means what? With better process, we can reduce the chip size for DEC, but not for ADC. It means what? ADC is much more complicated. than our imagination. So you have no way to reduce the chip size. You need to have some kind of trade-off. Increase the chip size with better, even with better processes. You still need to sacrifice more chip area to get good enough accuracy. And this is the reason why for the same best wild IC design house, no chip area reduction with better processes. No scaling can be seen. Okay? All right. This is the end of today's class. Thank you.